Hello.
Yes, sir.
Acha, thank you. All right. So was it clear to everyone that today is the tutorial? Some confusion was there in my previous emails, but was it clear?
Yes, sir.
Okay, thank you. So let me share the whiteboard and we will start solving our tutorial today. Is whiteboard visible to everyone? Is it visible to everyone?
Yes, sir.
So we start with a new whiteboard page. Let me copy the tutorial number 7. Okay. So is it visible to everyone? So what is been given in our problem is maybe I'll just let me rephrase everything and just a minute. Let me rephrase everything. Okay. So the problem given is this. A 4 centimeter diameter of steel ball with density of 7,800 kg per meter cube and specific heat of 473 joule per kg per degree Celsius at 90 degrees Celsius is suspended in a steel air at 25 degrees Celsius. If the ball cools down by free convection is nothing but natural convection. Free convection heat loss only. Calculate the time required for the temperature of the ball to drop down to 35 degrees Celsius. Okay, so we have to calculate the time required for the ball to cool down to the temperature of 35 degrees Celsius. Initially the ball is at 90 degrees Celsius. So we had this steel ball we are having. Initially temperature T1 is, let's say, 90 degrees Celsius. Okay, ambient air temperature here TA is 25 degrees Celsius. We have to find T when T2 becomes 35 degrees Celsius. This is what the problem is, correct? Again, the diameter, this diameter is given. This diameter is given as 4 centimeter. So problem is clear to everyone? Hello?
Yes, sir.
Now, in this particular problem, the only complication comes here in order to consider the properties. Okay, remember when we are having the free convection, natural convection, remember all the properties of the fluid has to be calculated at average temperature. And what is that average temperature is? Can anyone tell me? So that is the notable difference. Very, very often we don't look at this difference carefully. So when we are looking at the free convection and when we are looking at the forced convection, in both the cases, average temperature has to be used for properties, but the average is calculated differently in both the cases. Okay. In a forced convection, average is calculated with respect to the fluid. So fluid which is present at one end and the fluid is present at the another end, average of that those two temperatures is taken as a average temperature in case of the uh, forced convection. But in a free convection, in free convection, fluid is not moving. Fluid is not at all moving. So the temperature here is taken as the wall temperature and the bulk fluid temperature. Average of that is taken as the average temperature. Okay, this is the small difference. Is it clear to everyone? Is it clear?
Yes, sir.
So in this case now, initially this ball is at 90 degrees Celsius and the ambient is 25 degrees Celsius. So initially the average will be what? Initially the average will be 90 plus 25 divided by 2, isn't it? Do you all agree? Do you all agree? Isn't it?
Yes.
That is what the surface temperature of this ball is, 90 degrees Celsius initially. Ambient temperature is 25 degrees Celsius. So average of that will be the initial average temperature. But this average temperature itself is changing, isn't it? Remember, this T1 is continuously decreasing. Eventually, this T1 will become T2. Can you see the point? So taking the average temperature is not easy in this case. Does it make sense what I'm trying to say? Hello?
Yes, sir.
So in this case, this is the one extreme. This is the extreme one, isn't it? This is the extreme one. This is the extreme one. What will be the extreme two? Extreme 2 will be 35 degrees Celsius is the surface temperature, 35 plus 25 divided by 2. This will be the another extreme for average temperature, isn't it? Correct. And since this average temperature is varying across the time, if I take extreme 1, that is also not correct. If I take extreme 2, that is also not correct. So the best way is to take the average of both. Isn't it? So my average temperature will be what? 90 plus 25 divided by 2 plus 35 plus 25 divided by 2, and this entire thing is again divided by 2. So this comes around 44. Is it clear to everyone? Is it clear what we are doing and why we are doing? If something
Yes,
is not clear, please say. Okay, if something is not clear, please say this part is not clear. We will discuss it again. Is it clear? Anyone?
Yes, sir.
Makes perfect sense.
Yes, sir.
Okay. So once we have found out the average temperature, I have given these properties directly at 44 degrees Celsius for convenience, but in general these values will not be given. What we have to do is first find out this average temperature, then go back to the tables which are there backside of the book. There two tables are given. One table is for water and another table is for air. Okay, in this case you can take the properties of the air at this temperature and you can write down those properties. So these are already given here for convenience. So let's solve the problem now based on this. So in this case, in the problem itself, what we have been given is there is a natural convection taking place. And based on the natural convection, the heat dissipation is taking place, isn't it? So first we have to calculate what will be the heat transfer coefficient, isn't it? And that heat transfer coefficient, then we have to use it in a unsteady state heat balance in order to find out the time. Do you all agree with me? Do you all agree with me?
Yes, sir.
So see, what will be the balance in this case? The balance in this case will be the internal decrease in the internal energy of this ball will be same as the amount of heat taken by the natural convection. Yes or no? The balance in this case will be this mCp dt by dt, isn't it? This is nothing but the change in the internal energy of this ball should be equals to the heat dissipation by convection, isn't it? So heat dissipation by convection will be do you all agree or not? This will be the balance equation. So from this balance equation, we wanted to find out the time required for changing this temperature T1 to T2, isn't it? 35 degrees. That's what we are trying to find out. But in this case, everything is known. This mass of the ball we can calculate. Cp is already given. Area of the ball also we can calculate. T and TA, these are all are there. The only unknown in this case is H. Yes or no? Unless and until we know this H, we will not be able to calculate T, small t. Do you all agree?
Yes, sir.
So in this case, we need to find out the value of H means what? What we have to do? We have to use the correlations, isn't it? The other way could be we write the balance equation from the first principle, solve the velocity profile, find out the boundary layer around this entire ball and solve the complicated energy equations and flow equations to get the values. But that's going to be cumbersome, isn't it? So instead of that, we can directly find out H using the correlations, correct? So let's find out H using the correlation. So what correlation we can use in this case? There are different correlations are there. And all these correlations in the free convection are with respect to what? These are with respect to Nusselt number is correlated to Grashof number and Prandtl number. Remember? In a forced convection, Nusselt number is correlated to Reynolds number and Prandtl number. In a natural convection, Nusselt number is correlated to Grashof number and Prandtl number. Or in some cases, instead of Grashof number, we use a Rayleigh number. Both are okay. Do you all agree with me? That is what we have seen, isn't it? If I go back to the slides, maybe I'll just show so that you can appreciate what we are discussing here. Let me open the slides. You know, that is what we said, isn't it? Nusselt number, HL by K will be a Nusselt number will be given by the Prandtl number and Grashof number. Very often we represent even a Grashof number so different correlations also we have seen, isn't it? And in this case, the ball we are looking at. So free convection from the sphere. This is what the equation we can use. Do you all agree? Yes or no? This is the free convection from the sphere, isn't it?
Yes, sir.
So this in this particular correlation, what we have used, Rayleigh number and the Prandtl number. Rayleigh number is nothing but what? Grashof number into Prandtl number is nothing but the Rayleigh number. So it's okay. Either I correlate with Rayleigh number or a Grashof number, it doesn't matter. So that is what has been given in the problem here, isn't it? So this is the correlation which we are going to use. So let me again go back to the whiteboard. Okay. So in this case, first we have to calculate the Rayleigh number. So Rayleigh number is given by what? Rayleigh number in terms of diameter is RAD, that is given by G beta delta T D cube by nu into alpha. This is what the Rayleigh number is. In terms of Prandtl number, if you wanted to write down in terms of Prandtl number, this is given as G beta delta T D cube by nu square into Prandtl number. This is what is the Rayleigh number. Remember, the Prandtl number is nothing but what? Prandtl number is nothing but momentum diffusivity divided by thermal diffusivity, isn't it? So if we multiply and divide by nu, in this case, if I multiply and divide it by nu by alpha, in that case, this will be nu square and Prandtl number will be multiplied here. Okay, so now let's put all the values. So in this case, G is 9.81, that is the acceleration by gravity, isn't it? Beta we can calculate. Remember beta, as I said, if you assume that the air is a ideal gas, for an ideal gas, beta is given by 1 by T, where T has to be calculated in Kelvin, and this T has to be what? This T has to be the average temperature, because all these properties we are finding out at average temperature, isn't it? So that means beta will be given by 1 upon 44 plus 273.15. So this will come around 0.00315. Check whether this is correct. The other properties are already given. This kinematic viscosity is given as 1.75 into 10 raised to power minus 5 meter square second, and thermal conductivity is also given, that is 0.0276 watt per meter degree Celsius, and Prandtl number is also given. Prandtl number is given as 0.695. Okay, so now let's calculate the Rayleigh number. So Rayleigh number RAD, in this case G is 9.81 into beta is 0.00315. Delta T is unknown in this case, isn't it? Because the temperature of the ball is going to decrease continuously, and we are not calculating the Rayleigh number at one point, isn't it? So this will be T minus 25. Do you all agree? Isn't it? Diameter of the ball is also given. So 4 centimeter is the diameter, isn't it? Diameter is 4 centimeter. So this is given as 0.04 cube into Prandtl number is 0.695 divided by nu square. So 1.75 into 10 raised to power minus 5 square. Okay, is it clear to everyone what we are doing? Now the correlation in this case used should be this. Nusselt number is given as 2 plus I'm writing the correlation 0.589 Rayleigh number raised to power 1 by 4 divided by 1 plus 0.069, sorry, 469 by Prandtl number raised to the power 9 by 16, and this entire bracket is 4 by 9. Okay, is it clear what we are doing? And this equation is valid for Prandtl number greater than equals to 0.7 and Rayleigh number less than equals to 10 raised to power 7. Okay, this is what now this equation we are using. But remember, what is the Prandtl number for the air? Prandtl number for the air is 0.695, which is very close to 0.7, isn't it? So it doesn't matter even though we are using this equation. So almost applicable. Is it clear to everyone? Hello?
Yes, sir.
So it doesn't matter. This slightly, it is almost 0.7. So we can safely use this equation without worrying too much. So Nusselt number will be hd by k. So this will be hd by k. So that also we can put h into d is 0.04, k is 0.0276. So this is Nusselt number 2 plus 0.589. So this entire thing we can calculate in terms of t minus 25. So if we calculate this entire thing, what we get is 4.48 into 10 raised to the power minus 3 t minus 25. This is what we are expected to get. Is it clear to everyone? Does it make sense to everyone? If you calculate, remember in this case, this t minus 25 is the unknown. All other things we can calculate. So you can calculate and represent in terms of t minus 25. So this is what expected to get. Check whether this is correct. Hello? Is it clear? So this we can put it here then in this equation. So 589 into the bracket 4.48 into 10 raised to power minus 3 t minus 25, and this entire bracket is 1 by 4 and divided by 1 plus 0.469. Prandtl number is 0.695. This 9 by 16, and this entire bracket is 4 by 9. So what ultimately we get from this equation is 2 plus 707 t minus 25 1 by 4. This is what we are expected to get, this entire thing. Okay, and if we rearrange this equation, h is calculated as, h will be given as 1.38 plus 2.558 t minus 25 raised to the power 1 by 4. This is what we are expected to get. Check whether this is correct. Hello? Is it clear what we are doing to everyone? Hello?
Yes, sir.
So are the values which I have projected is correct? Check whether these values are correct.
Yes, sir.
Everyone is getting the same values? Okay. So now once we have obtained H, then we can go back to the balance, isn't it? So what was the balance which we are looking at? We were looking at mCp dt by, so this is this sphere we are saying. So mCps dt by dt should be equals to HA T minus 25, isn't this is what we have to solve, correct? So let's calculate this mass. Mass of the sphere will be given by what? Mass of the sphere will be given by volume into density, and volume will be given by pi by 6 d cube, isn't it? This will be volume into rho s. So pi by 6 d is 0.04 cube into the density given in the problem is density of the sphere ball is given as 7800. So mass of the ball comes out to be 0.261 kg. So we can write down the balance now based on this. So minus 2.61 into specific heat of the ball is also given in the problem statement, that is 473 joule per kg per degree Celsius, 473 dt by dt. H is, we have just calculated, H is calculated as 1.38 plus 2.558 T minus 25 1/4. This bracket is H multiplied by area. So area of the ball will be what? Area of the ball. Remember outside area you have to take, so that is pi d square, isn't it? So multiplied by pi into 0.04 square, that is the area, into T minus 25. Is it clear to everyone? Now another question is why minus sign here? Can anybody say why minus sign here? Why this minus sign? Because the temperature of the ball is cooling down, isn't it? Temperature is decreasing. That's why this minus sign is coming here. Is it clear to everyone? As time progresses, temperature is decreasing. That's why minus sign is there. Okay. So now we can solve this integral. If you rearrange everything, what you are expected to get here is, if you rearrange everything, what you are expected to get is this. You will get this dt will be on this side, and this t minus 25 1 raised to the power 4, and again this t minus 25 term, this entire terms will be coming on the left hand side. So what you are going to get is, that minus sign is there. So we will switch. We will have this minus sign here outside. So initial temperature T1 is 90 degrees Celsius. T2 will be 35 degrees Celsius, and inside you will get dt, and the simplified part of this. So simplified part of this will be, if you calculate carefully, you should get T minus 25 plus 1.851 T minus 25 raised to the power 5/4. And here you will get 0 to T 0 to t 5.62 into 10 raised to power minus 5 dt. This is what you are expected to get. If you rearrange everything, this is what integral you are going to get it. Is it clear what we have done? We have just rearranged things, and since we are interested in finding out this actual temperature, we can integrate that. So after integrating, finally, this is what we are expected to get. Is it clear? Hello?
Yes, sir.
Yes, sir.
So now you can solve this integral again on your calculator. Solve this integral numerically on your calculator and tell me what is the value. Solve this integral on your calculator and tell me the value of. This is clear, isn't it? Right hand side will be directly, you will get it as right hand side, you will get it 5.62 into 10 raised to power minus 5t. This is what you are going to get it. What will be the left hand side? And then rearrange and calculate the value of t. Can anyone calculate and tell me? Anyone? Anyone got the value of time? Is anyone calculating?
So 0.36.
0.36 what? It's not correct answer. What you are expected to get is 6.484 seconds. Check whether you are getting this or not. This is what you are expected to get.
Yes, sir. Yeah. 6408.
6408 you are getting?
Yes, sir.
That's okay. Depending on how accurately you have calculated these intermediate values, some variation you will have, but around 6400 you will get the time. So everyone is getting the same value. Check whether you all are getting the similar values. Anyone has any other value? So 6484 seconds. That means how many minutes? 6484 divided by 60. So 108 minutes, and if I again divide by 60, so 1.8 hours will be the time required. 1.8 hours will be required for cooling down. Now try to think about it in a more realistic way. Where if you put a steel ball, same steel ball which we are talking about, in a ambient air, assume that the air even at a in your at a room temperature, will it take 1.8 hours, almost 2 hours to cool down? Will it take 2 hours to cool down almost? Is this number is realistic? Can anybody say anything on this? The number which we are getting, is it realistic? If I cool down a steel ball which is given in this particular example, the calculations are telling me that it is going to take 2 hours. But if I look at practical case, it is not going to take 2 hours, isn't it? If you take a tea, in your cup, that is the temperature is around, you are boiling the water, that means temperature is almost 100 degrees Celsius. It takes 2 hours to cool down to your room temperature.
No, sir. No, sir.
Isn't it? It cools down maximally by 15-20 minutes. You will be cooling down it to 35 degrees Celsius, isn't it? Isn't it? If we compare the realistic examples which we see every day in our life, it takes much less time than this. So where we are missing, what we are missing? That is the question. What is the point which we are missing in this entire analysis?
So maybe there is a bit of forced convection going on.
Yes, that is the reason. Yes. So in a real life situation, it's not the natural convection which alone is present. There's a forced convection is also there, isn't it? So air is not completely stagnant. It's moving, isn't it? Maybe some fan is on, some air is moving here and there. So forced convection effect is also important. So if you include that forced convection effect in this, you will find that the time for cooling down is decreasing. It will not be 2 hours. It will come around 25 minutes or even less than that, 20 minutes or something. Does it make sense to everyone? Hello?
Yes, sir.
So if you solve the same problem, assuming that the natural convection as well as forced convection, both the regimes are present, if you start solving with that, your mathematics is going to become complicated. But just for a practice sake, if you solve it, see how much time decrease is there, isn't it? Does it make sense what I'm saying? So in that case, what you have to do, you have to calculate the H. Not only H will be a combination of forced convection and a natural convection. Remember, we have seen some correlations for that also, isn't it? If I go back to, let me just go back to the slides. Maybe that will, that will put some more light on what we are discussing. So remember, towards the end, we have said that this is what we said, isn't it? When both the regimes are present, in that case, the heat transfer, heat transfer coefficient can be calculated using this particular formula, isn't it? So you will see that your heat transfer coefficient will be much more, much higher compared to what we are calculating now. Does it make sense to everyone?
Yes, sir.
So almost you will get 10-15 minutes or 20 minutes maximum. That will be the time required for cooling down. It will not be a 2 hours the way we are getting, because in this particular example we have ignored the effect of forced convection completely. That's not the reality. OK, but in real cases we will have much lower time than what we have seen in our answer. So this is a overestimation. The obtained value is a overestimate. As forced convection effect is neglected completely. Okay, so we stop here unless you have any question. Is it clear to everyone what we are discussing? Is it clear? Does it make sense? Is there any question? Hello? Is there any question? So
No, sir.
if no question is there, let's stop here. We will have a class tomorrow. Same class time. Okay, same class time. We will have a class, and then we will discuss about the quiz and all in the class itself. Okay. So most probably we will have a quiz offline. We have to see whether everybody is going to on board or not. Depending on that, we will decide whether we will have a quiz online or offline. Okay, I prefer to have offline, but if some students are not there, then it is not possible to conduct, isn't it?
Sir, what is the tentative week?
Tentative week will be, as somebody said, that up to 15th of March, everybody will be coming back, isn't it, in the campus? So we will have a quiz after that.
And then there is another more one after that. Because we are.
And the last one will be after completing the entire syllabus. So that will be first week of the April.
Okay, sir.
So just before the major examination, we will have one more quiz on the complete syllabus. I prefer to have it, offline. But if some, if some students are not available, then I have no other choice but to conduct it online, isn't it? All right. So we will discuss all these things in the next class. Whatever is suitable to everyone, we will, follow that. So let's stop here unless you have any question, anything to say. Can we stop? Okay, then see you tomorrow. Okay, all right.
Thank you, sir.
Thank you, everyone.